So good morning, everyone. My name is Yoko Kawamura. I'm a first-year PhD student. So today, I will give you two talks. The first talk is accurate determination of the intrinsic diffusivities of boron, phosphorus, and arsenic in silicon, the influence of silicon dioxide films. Okay, let's start my presentation. First, I will begin with the introduction. Recently, the channel length of MOSFET has been scaling down to nano-order. For fabricating such shallow junction devices, the diffusivities of the impurities such as boron, phosphorus, arsenic, which are used for the dopants in source and drain region, are very fundamental and important values. However, previously reported values of the intrinsic diffusivities do not agree with each other, and we found that these can be separated into two groups. And the pink line was reported in Journal of the Electrochemical Society in 1975, and the purple line was reported in Applied Physics Data in 2003. And this difference between the two values, we think, depends on the existence of the surface silicon dioxide films. And we found that we determined that the diffusivities of boron and phosphorus and arsenic in this study. So I will explain experimental method. First, the samples where the silicon dioxide films on the surface, grown on the surface, were prepared, and then boron, phosphorus, arsenic ions were implanted into the samples with the condition as shown in this table. And then samples were annealed at 950 degrees for 30 minutes to remove the damage that would cause a transient enhanced diffusion. And then the distribution of the impurities measured by secondary ion mass spectroscopy. And then these samples were separated into two kinds. The one is named samples with silicon dioxide, where the silicon dioxide films were remaining on the silicon surface. And the other is samples without silicon dioxide, where the silicon dioxide films were removed by HF treatment. The thickness of silicon dioxide of the samples with silicon dioxide was, at this time, 18 nanometer. On the other hand, the samples without silicon dioxide, almost 0 nanometer. And diffusion annealing took place for all of the samples at 800 degrees to 1050 degrees for 0.25 to 84 hours in the atmosphere of 99.999 argon pure gas. And then the distribution was measured by SIMS again. So move on to the result and discussion. So here, this figure shows boron depth profiles before and after diffusion annealing. The y-axis boron concentration and the x-axis is depth. And the black line is the profile before diffusion annealing. And the red and blue lines were the profiles after diffusion annealing of the sample with silicon dioxide and without silicon dioxide, respectively. Anneal is done at 900 Celsius degrees for 12 hours. And this figure shows boron diffusivities obtained from the depth profiles. Boron diffusion in the samples without silicon dioxide was larger than that in the samples with silicon dioxide, and this tendency was consistently obtained for the different diffusion annealing temperature. this is boron diffusivities from these depth profiles as a function of the inverse of diffusion temperature. Red is with silicon dioxide, blue is without silicon dioxide, and we obtain different diffusivities between the two kinds of samples. And okay, I will explain why we have the difference. This can be explained by oxidation enhanced diffusion, or OED. So I will explain what OED is. When oxidation was occurred on the silicon surface, the silicon dioxide silicon interface here is strained because the volume of silicon dioxide is larger than that of silicon. Therefore, excess silicon interstitial at the interface are generated and diffused into silicon substrate. And these silicon interstitials enhance impurity diffusion. In the case of samples without silicon dioxide, very small amount of oxygen existed in the inert atmosphere, grew the silicon dioxide films on the silicon surface. In spite of our best effort to avoid leaking oxygen into the silicon substrate by flowing 99.99% very pure argon gas. This oxidation caused oxidation enhanced diffusion, as I mentioned in the previous slide. On the other hand, samples with silicon dioxide, these films prevented oxygen from reaching the interface, and oxidation enhanced diffusion was avoided. In fact, the thickness of silicon dioxide films on the samples with silicon dioxide didn't change between before and after diffusion annealing. On the other hand, we found the growth of the 3 nanometer thickness SiO2 on the surface of the samples without silicon dioxide. So oxidation enhanced diffusion caused the difference I showed. And then, moreover, when our diffusivities are compared to the previous works, this red line with silicon dioxide results agree with the value reported in 1975, and the samples were used for this study had silicon dioxide on the surface. On the other hand, this blue line without silicon dioxide result agreed with this experimental value, and the samples used for this experiment had no silicon dioxide films on the surface. So what we can say here is that intrinsic boron diffusivity was obtained from the samples with silicon dioxide. For phosphorus diffusion, the same tendency as boron was observed, like this. So we obtained intrinsic phosphorus diffusivities from the samples with silicon dioxide. For arsenic diffusion also, we obtained the same tendency as boron and phosphorus case, but much smaller difference between the diffusivities of samples with and without silicon dioxide was observed. This is because arsenic diffusion in silicon cause not only bare silicon interstitials, but also bare vacancy. And this is, and then oxidation enhanced diffusion is less affected compared to boron and phosphorus. Let me summarize my talk. we determined intrinsic diffusivities of boron, phosphorus, and arsenic from the samples with silicon dioxide on the surface. And we found that silicon dioxide films on the surface prevent oxygen from entering silicon and silicon dioxide interface, which avoid oxidation-enhanced diffusion. And the difference between arsenic diffusivities from the samples with and without silicon dioxide was smaller than that of boron and phosphorus, because arsenic diffusion is arsenic diffuse B of both silicon interstitials and vacancies, and as a result, arsenic diffusion is less affected by oxidation-enhanced diffusion. Thank you for listening.